Okay, I'll just introduce Daniel here, Holbleck. He's from the University of Calgary. He's a professor there in the physics department for quantum. We've been working with Daniel's department for quite a long time. Since 2015, we've supplied them just with some fiber optic cable for them to do their entanglement experiments, and we're still working with them for providing them that infrastructure for them to do their experiments. But Daniel's here today to do his presentation, so I'll hand it over to you.
All right, thank you very much. I think, can everybody hear me in here? Or is it for the online? I see, yeah, that makes sense. All right, so thanks again for the invitation to present here. And as Dave mentioned, we've had a long collaboration with the City of Calgary and still have it. And I think, you know, the Calgary has been visionary in many ways of how they build out their infrastructure and make it available to us. So what I'll be giving today is, you know, quantum communication in Calgary. So it's a mix of a couple of different experiments over the years. So I had to dig up some older talks and some newer talks and blend it all together, because what I really want to show is a little bit about what kind of things we've been doing in Calgary, what's the history of quantum communication research in Calgary, and you know, highlight also the parts where the city has been involved. So let's get started. Quantum in Calgary has been around for a while. So the Institute for Quantum Science and Technology was founded with a slightly different name in early 2000s. And right now we have a lot of research groups, and we're expanding greatly with roughly over the next couple of years here, doubling the number of faculty members over different departments from math, chemistry, engineering, physics, and computer science that work in quantum, in the field of quantum technology and quantum science. And we also have some a foundational center called Quantum Horizons Alberta, which is starting up, where we'll be doing very foundational research in quantum. We have Quantum City presenting later on today, so I won't talk too much about that, but lots of initiatives from a clean room to events to a professional master sponsored by by Quantum City. I myself am a prof, as Dave said, at the physics department at the University of Calgary, and I called my lab the Quantum Cloud Lab. Because we're building a quantum cloud. If you want to look us up on social media, there's a couple of things. And this is a photo that I myself took. So when I go abroad, I always show people how beautiful Alberta is, and hopefully that will attract some people to here too. Here's who we are. This is our stint at being structural engineers. We're trying to see when this bridge will break. So far, so good. So we'll keep expanding. Now I know that you've had some presentations on what is quantum, so I won't go too much into detail about that. So thank you, Kubo, for doing that for me. I will, you know, just to give as everybody on the same page, say that, well, what is quantum mechanics? It's the theory of really tiny stuff, generally speaking. Of course, there's no, in principle, limit to how big quantum systems can be. Hence, Schrödinger's cat is the famous sort of thought experiment, but it's not realistic to have that large systems acting quantum mechanically. So generally, it's all the small things. What is quantum information then? Well, quantum information is taking the principles of classical information theory, where we have zeros and ones stored or communicated or dealt with for processing on these classical devices there. Hint, some of them actually use quantum mechanics as well, of how they work, but the information is stored classically. And then we say, well, let's see if we can put that over into some sort of a quantum system. And when we do that, we enter a realm where bits become qubits, and we have these states where we have zeros and ones, just like classical bits, but we also have these wonky things here that are superpositions, where we have 0 plus 1s or 0 minus 1s, and they're all different. And we can encode them into, let's say, different energy levels of atoms, or we could choose polarization states of light, and we can say that as long as those two are orthogonal, they can serve as zeros and ones. So if you measure 0, it's a 0, and you measure 1, you know it's a 1, right? But the superpositions is what really makes it unique. And so what is a quantum communications network? Because that's what I'll be talking about. So very broadly, we can say that it's some sort of a system that facilitates the distribution of quantum states over a distance. So one thing is to have these quantum states in one place. Another thing is to share them with your friends or enemies or whoever, and doing that over some amount of distance. And that's sort of the essence of the research that we do, is to create these states, to transport them, and then to measure them. So, you know, what is a quantum network? Could it be photons that are emitted from a single atom decaying over, and then moved over, let's say, a free space channel or fiber? Yeah, that would work as a quantum network. We can encode quantum information into these single photons. But sort of a laser death ray, too many photons, not quantum, very classical, okay? So we have to be at the very weak, very dim light level. Put an atom inside a box and ship it, you know, if that box also contains a cryostat or something like else, you know, well, it could be a quantum network. You could build a quantum network where packages are just sent between different places in the world, as long as you can keep your this atom, very, very isolated and nicely. Whatever this is, not a quantum network, you know, very classical. Although interesting sideline here is that birds actually use quantum mechanics to navigate. So they have magnetic sensors in their head somewhere that sense the magnetic field. So maybe a little bit of quantum still in there, but not communication, sensing. Okay, so of all the things we talked about, the most practical still for transmitting quantum information is going to be light. And why is that? Light, as in photons, when we go to the single, very, very dim light level, is that, you know, as we know, photons, light is really fast. It doesn't actually interact a lot with its surrounding. It's very easy to isolate. And then they have a lot of things that we can use to encode the zeros and ones. We call those degrees of freedom. The polarization will be one of them. So polarization, as I said here, we have the horizontal and vertical. And if we create superpositions of a horizontal and vertical, depending on the sign between those superpositions, we can have diagonal or an anti-diagonal polarization. So depending on how we make those superpositions, we can encode, or how we rotate the polarization, we can easily encode different polarization states. And we also actually, right over there, I think there's some polarization elements, some rotators, so we can, you know, manipulate polarization. Very easy way to encode quantum information, very easy to understand, and the one that's also was used in the beginning for a lot of quantum information work. We actually prefer to work with something else, which are called time bins, where you encode quantum bits into an early or late arrival time, and then we create superpositions of early and late. Sounds weird that you can do that, but basically when you don't know something about a photon, it's as if it's in a superposition. So if you've split a single photon in two and then merged them into the same path, then you can not know whether it arrives early or late. So you can create these things as well. There's different ways to encode quantum information, and these ones tend to be more practical for us. Okay, so how do we then transport these photons that have encoded our quantum information? Well, we can choose one of two ways. We can go, just generally speaking, we can go through an optical fiber, and of course this is very convenient and practical, and there is fiber networks all around the world, including here in the city of Calgary. We could also choose to go over a free space, just shine a laser beam, dim it very much, which obviously has some problems because you can't have obstacles. Most people believe that there is a curvature of the Earth. give or take a minor small percentage. And so there's a limit to how far you can go in a straight line as well. We'll get back to that later on to see where this free space communication actually comes into play. But for the moment, we're going to talk about the fiber optic channels. And the one thing to note is that even though fiber optics is very good, they do actually lose some of the light. So there is a bit of scattering of light. It's down to sort of 0.142 dB per kilometer, so it's very small, but it is there. And this is at a specific wavelength as well. That is the optimal one for telecommunications. So how we choose to transmit our light is going to determine where we want to go. In essence, how far we want to go. So before I dive into that, let me just briefly touch upon the use cases of quantum communication networks. I think some of it was touched upon. We talked about, quantum key distribution, which is a way to exchange cryptographic keys that does not rely on mathematical problems, or the hardness of mathematical problems. So the kind of cryptography that you're able to implement this way is what we call information theoretically secure, as opposed to being computationally secure. The problem with the current cryptographic systems is that the protocols offered by quantum computers would actually be able to break them if the quantum computers are large enough. Of course, quantum computers are also being built, and you may have only so many quantum bits in a single, or quantum processors on a single system, and you might want to connect them to have a larger system, and in that case you need a network. And we all can appreciate how the internet enhances our experience with classical computers. And I don't think that people back in 20, 30 years ago could quite have imagined what the internet has become today. And I think similar to that, we can come up with some ideas here, but I don't think we can quite imagine what a quantum internet would do for quantum computers. But a lot of it circles around security. There are certain things you can do privately, securely, in terms of connecting quantum computers over a quantum internet or a quantum network that are just different than anything you can do classically as well. And then we talked about quantum metrology or quantum sensing more broadly, again, where somehow doing measurements that are distributed over a large distance enables you to increase the sensitivity of those measurements. And sort of, if we could illustrate quantum networks with one sort of like, with one picture, it could be maybe something like this. Let's start with the fact that those who are not familiar with Pokemon, this is a turtle. So a turtle is rather slow, right? So quantum networks are not particularly fast, but it has a shell. So it's pretty secure, like more secure than other networks. And then it's a Pokemon. So you do something to it, you call it, and it has some very special magical properties. So that's how you can envision a quantum network being. Slow, secure, and a secret sauce. Okay, so this brings me to the highlights of quantum communication in Calgary. And here's where I'll touch upon some of these applications and some of the methods used to transmit, but in this context of the quantum communication as it evolved here in Calgary. Okay, let me get a sip here. So, quantum communications came to Calgary, at least the experimental part of it, roughly in 2006. So, in that point, the Quantum Communications and Cryptography Lab was founded by Professor Wolfgang Tittel, who came from Geneva, where they had a lot of quantum communications research going on. In fact, some of the first QKD experiments were done from Geneva to some neighboring cantons or cities using QKD as a first time. So the group here was started around 2006, and I think this picture is from 2008 or 2009, which is just before I came to Calgary. A couple of important experiments and demonstrations were done at that point. So the first, task that's really important is to move these types of experiments out of the lab and into the real world. And in the real world, you think it's just the same as the lab, but there's a whole bunch of challenges that you're faced with in terms of stability and in terms of actually communicating and linking up all your equipment over a long distance. So the first effort, or some of the first efforts, were towards getting a real-world link. In this case, in the beginning, it was a link between the University of Calgary and SAIT, so it was a joint research project between those two institutions. And the first thing they did was to implement this BB84 protocol. It's named after Bennett and Brassard, and Brassard is from Montreal, so one of the first quantum communications or quantum cryptography protocol that was proposed, and the one that's sort of the hallmark of most quantum communication. So I don't remember, was this introduced earlier today, BB84? No, we were more high level. So I'm not going to talk too much about it either, because it take a long time. So let me see if I can distill quantum cryptography protocol in like a minute or so. We are familiar with the bases, right? So we have these different bases of photons, and they can be encoding zeros and ones, and depending on the basis, we can say that the vertical and horizontal encode zeros and one, or the diagonal and anti-diagonal encode zeros and ones. And the main thing to know about quantum mechanics, which I think was covered, is that it's probabilistic. So if you have a single photon, it has to decide whether it is a 0 and 1 when you measure it in some way. And so where Alice, who is sort of the archetypical sender of quantum information, encodes these four different states, Bob just chooses a basis to measure in. And if he measures in a correct basis, so let's say it's the horizontal vertical one, then he will know exactly get exactly the right outcome if Alice also prepares in that basis. And same way in the diagonal anti-diagonal, if Bob chooses the correct basis, the same one as Alice used to prepare her bits, he will measure 0, 1 correctly. If they choose different bases, Bob has a random outcome. He can measure anything because it's completely random which outcome he measures in that case, because it's an equal superposition in that case. So what that means is that if they choose these bases and the preparation bases and measurement bases randomly, half of the time they'll choose the wrong one. And those or do not match up their choices, and in that case, we just discard them. In the cases where they choose the same basis, Bob should measure exactly the correct bits that Alice sent. But the problem is then for an eavesdropper who wants to intercept this key, that they also have to choose a measurement basis. And when the eavesdropper chooses the same basis that Alice and Bob chose, then they can get away with stealing the bit. But if they, as they will half of the time, choose the wrong basis, well, in that case, they get an outcome, but when they try to recreate that photon and sending it onwards, they recreate the photon in the wrong basis, and now Bob's measurements are random. And if they're random, that means that half of the time he gets out the wrong measurement results. So if you kept track of the probability, was half of the time, so 25% of the time, Bob will be detecting the wrong bit values. And if they compare that afterward, a subset of them, they can see that somebody is causing excess errors on their link, and that is how they can verify, well, they can detect if somebody is trying to steal the key, and if so, they just don't use that key to transmit a message. And if it all clears, well, they go ahead, use that key, they've verified that they now have a shared secure bit string, and that's what you need for encryption. All right, a little bit more than a minute, but close. So this system was then implemented through a fiber-optic link between Calgary and SAIT in 2009. Maybe 2008 was when it was done, but then it was published in 2009. And here's an example of the system. We see some transmitter box here where they prepare the states. That's this part here, and then here they have a receiver state, and these 4 big chunky boxes here, those are the detectors that were used at that time. And was published here in 2009. And here is an excerpt from the paper as one of the figures. Calgary and SAID, so literally put Calgary on the map. And excuse me, a lot of the studies were about looking at how the state fluctuates depending on the outside temperature. And it's always nice to see that you're in Calgary when you're plotting like -16 and stuff like that, right? We always try to measure on the coldest days of the year just to show off how tough we are. The problem with this protocol, though, is that the detectors, they're vulnerable to attacks. So people have found out that even though the protocol in principle is secure, you can try to find weakness in how the experiment is realized. For example, you're assuming the detectors measure single photons and click in a certain way, but then people like this come around. This is Vadim Makarov. He used to be at IQC, right? And he has the looks and the logo and everything. Now he's elsewhere, but he was behind several of these attacks on the QKD systems. And if you look sort of at the list here, you see that a lot of them are on the detector, right? So the detector is clearly the weakest part of the system. So is there a way to implement a quantum key distribution protocol that is not that's resilient to these attacks on detectors? And it turns out there is. And it's called, very imaginatively, measurement device independent QKD. So, warning, a few equations up ahead. Don't worry. You don't need to. I'll try to not talk to the equations, but for all the nerds, you can say that you went to a talk and you saw lots of equations. So here we are. What is measurement device independent QKD? Well, we have Alice and Bob. They're the usual culprits that want to communicate some secret. And again, they choose to encode their information in different bases. We have the plus basis, horizontal, vertical, or this cross basis where it's actually diagonal polarizations. And they then enlist the help of Charlie. And what Charlie does is that he measures on one of these states here that's listed up there. So we have 4 states in total with the plus minus is taken into account. And those are the Bell states. So they're what we call maximally entangled states. And what you can see, the way to understand this notation, and we'll focus on the psi state here. We love Greek letters, by the way, So what this means that if one of the people measures an H, the other one has a vertical polarization. And if the other person measures a vertical polarization, the other one has a horizontal polarization. So once you measured one, you know what the other one was. And so instead of creating this state, Charlie, he measures whether this is the measurement outcome. And what you can see from this is that once Charlie measures, say, the psi plus state, it shows that Alice and Bob sent the opposite value. They sent the opposite bit value. One sent horizontal, the other sent vertical. But you can see both things are possible, so nobody knows who sent what. And that's the key of this protocol, is that all you're establishing is in which way were the two transmitted qubits correlated, but not what they were. So you can go through sort of a matrix here of looking at all the different possibilities of what Alice and Bob sent and what is measured. And as I said, we don't want the ones where they use different bases, so we skip the bottom ones altogether. And then we see that, well, if Alice and Bob sent Alice sent H and Bob sent V, there's a 50% chance of them measuring one of these. And they know that when they get this measurement outcome and they use this basis here, that they need to flip their bits because they're different. And so they can establish, just decide who flips the bit, and then they'll have a shared key. They'll know what the other one sent. But if you turn these around and say VH, it's the same result. But when one of them flips the bit, then it's the other value that they end up with. And for the other ones here where they have superpositions, there's also some probabilities that allow them to either do a bit flip or not a bit flip. And in the cases still, they can figure out between themselves what is the agreed upon shared key. And all that Charlie knows is that there was this correlation, but he doesn't know what each of their bits are, and so he cannot get access to the key. And that means that even if he goes, you know, sort of like rogue and becomes untrustworthy, he cannot get access to the key. And so for that reason, we call it measurement device independent, because it doesn't depend on who controls the measurement device. So this was done, this was proposed a few years earlier, I think around 2010, by a researcher from the University of Toronto, and was then implemented here a few years later, again, over a real-world link. You can see now there is still the link from U of C to SAIT, and then an additional one to the Foothills Medical Campus, because we need 2 senders and then a station where the measurement is done, Alice, Bob, and Charlie. Again, some publication came out of that. Nowadays, we're still working on that, and in terms of commercialization, this is the startup or spin-off company that we have, founded a few years ago, called QTI. And you know, one of the things that we're doing is that we're establishing these correlations over long distance using this protocol. But more broadly, the spin-off is about building quantum networks. So this can be used as a stepping stone to create a quantum internet. And this is, will find us over in the research park at the University of Calgary. Okay, then, continuing with the history, in 2013, something really interesting happened. We got these new detectors. They're called superconducting nanowire single photon detectors, or SNSPDs for those who don't speak too fast. So they are excellent in terms of 90% efficiency and very small dark counts, and they were a game changer in terms of what you could do, because suddenly now you could have a very large signal, every single photon was counted, and very little noise. So this was a severe limitation previously, and they're tiny. The only problem is they have to go cryogenic because they're superconducting, so we operate them below a Kelvin. But you can pack many into a single cryostat. This was done in a collaboration with NIST and JPL in the US. And so now we could do a whole bunch of new and interesting experiments. One of them was quantum teleportation. And this came about in a collaboration with the City of Calgary. So here's the link that we had. Oh, I didn't know it would cut it off here. All right. We had now different locations within the city, and I'll show some more pictures. One of them was right over here under the concert hall, Arts Commons. The other one was down at, what was it again? The data center down in M something, Manchester, there it is. And so altogether, we had these links. And so we did quantum teleportation, and we got at least a mention here on the front page of Nature Photonics, which is, you know, where people go to see. And so what is quantum teleportation? Well, let's start with what it's not. It's not this. Okay, not this, sorry. What is quantum teleportation? It's still weird. It's the disembodied, complete transfer of a quantum state. So even physicists puzzle with that, some of the famous ones, right? So disembodied means that no particle is actually exchanged in the direction that the quantum state is transferred. So it is a way to transfer the complete quantum state, which is something you can only typically do if you actually send a quantum system from one state to one place to the other. But in this case, it happens by, at the time that you do a measurement, and send the result of that measurement classically. Okay, let's see if we can illustrate what this means by a little use case. When might you want to use quantum teleportation? So here's Bob. Bob's earned some money somewhere in the, maybe in the resource business there, so he has a truckload of it, and he buys an expensive quantum device, you know, quantum computer or something really expensive. He loves it. It's very personal and important to him. And then Alice comes, and she would like to use this quantum device. And who doesn't trust a little girl with a shotgun. Well, Bob doesn't. He doesn't trust her. So he doesn't want to give her access, right? So what can he do? He still sees the business opportunity there for Alice. She's got some money too, and he likes money. In comes Charlie. Charlie, he's industrious, and he says, I have an idea. I'll facilitate the connection. And he tells Bob all he has to do is he has to install a source of entangled photons in his lab. And that source of entangled photons will take one of the photons to his expensive quantum device, and the other one he's going to send out. Notice that in this case, no information is going into Bob's expensive quantum device. So now he's more relaxed. I think he can do that. And that is what quantum teleportation essentially is. We end up in a situation where there is the Charlie's measurement here on the state that Alice sends to him, and part of this entangled pair that Bob sends to him transfers her quantum state into this device here, or onto this photon that's here. So that is actually what quantum teleportation is, and this is maybe one dreamt up use case of that. There could be others, but again, it has a lot to do with security. And, you know, she could enlist other users of quantum information. We're actually coming up to Halloween, so I guess it's very appropriate, right? So here's the quantum teleportation experiment, again, now with the actual location down in Manchester listed. And very, very, very quickly, here's what we did. We had these 3 locations, very close to City Hall. People outside of Calgary don't know. Then the Arts Commons building is not as easy to visualize. So these are, and I think this is just a generic building to represent the data center. I don't think it looks like this. So Bob has these 2 entangled photons that he then sends one of them, creates them in the lab. This is the setup. We call them B1 and B2. For those oldies will know what this is. And then we send one of them over the link towards Charlie. And at the same time, Alice prepares a qubit that she, or some information that she wants to transfer to Bob. They come together and they meet over at, oh, this is actually the location there at the, inside the data center. And they meet at Charlie, which was over in the Arts Commons building, and then he performs this joint measurement. And again, here's what that lab looked like down in the basement, just under the concert hall. And now the state has been transferred. And again, we use these superconducting detectors. Here's the cryostat, and here's the compressor for that. So lots of fun. Here's our moving business here, temporary quantum moving business, I guess. Again, everything in the back of the van. And now I was part of the whole thing as well. And, you know, here we are in the bottom of the basement, setting things up, trying to get things working. Have a little cart there in the data center and making all the people in the city nervous about what on earth are we doing there. And this does not look safe. But it was. So the aftermath, because what we learned is that, well, if you take Einstein and mention him somewhere and you put some science fiction in, akin to this, you get a lot of attention. And so this is the kind of attention we got, you know, most of it good, I think, you know, we were on the news, we became one of the top news stories from that year from out of Calgary, and, you know, around the world, it just kept creeping up with the weirdest of stories, you know, from all over the place. And this particular one here from MTV News, for those of you who know what that is particularly interesting because of the category that it was listed under, which if you look up to the far left there, I thought was really peculiar. So who knew that that was a category? So all fun and games. Let's just circle back to this discussion about the distance. How far do you want to go? So if you're going over not so long distance, so let's say you're within 100 kilometers, about 1% of the light is going to come through just because of the attenuation through the fibers. And we can live with that, you know, 1% loss. The way that quantum communication protocols are set up, you know, of course it's going to reduce the probability of your light coming through and your rate of exchange of information, but it's doable. But if you go to much longer distances, let's say you go somewhere above 2,000 kilometers, here's 2,000 kilometers as an example, your transmission becomes ridiculously low. You can wait something comparable to the age of the universe for a photon to come through. So that's not quite acceptable for most people. So we need to find some other ways to do quantum communication in those ways. And there's a couple of different approaches. If you want to go really long, there is a cheat sheet. The cheat sheet is to build a network that's made up of nodes that decode the information from the quantum realm into classical and then back into the quantum realm. But you have to trust these nodes, because if somebody takes over that node and once the information is classical, it's all accessible, well, then you have a problem. Somebody could steal it, you know. So where do they implement it to the largest is in China. So they have this whole backbone network of quantum links, this trusted node network. And the one thing you could say about that is that, of course, it is a stepping stone towards a more broad or more general quantum network that doesn't rely on trusted nodes. You put in some of the infrastructure and it's ready. And other places in the world, same approach is used as sort of this stepping stone. Another thing is to change the way that the loss occurs. So instead of having this scattering loss that causes an exponential decay of your signal, let's try to work with a different kind of loss. And where we don't have loss would be in a vacuum. If you send light through empty space, it doesn't scatter, it doesn't get lost. And so where do we have vacuum? Well, 10 kilometers or 50 kilometers up, we have more or less a vacuum. It's called space. So that's the notion behind space-based quantum communication. The only loss you do have is the fact that all beams expand. So if you have a beam, its mode, its size will expand, and that of course looks like you lose some of the light because it's not hitting your detector anymore. But that goes with the square of the distance, because the area grows with the square of the distance. So that's much better than exponential. Realizing that, we come back to the Chinese. They sent up the Mishi satellite in 2016 or 15 and published a whole bunch of stuff on that. You know, lots of groundbreaking experiments on quantum communication, entanglement distribution, and they have a network of these ground station and satellite ground station. And so we said, well, we should have some quantum networks ourselves. In fact, the Canadian quantum satellite mission, which was led by, or still led by, University of Waterloo, was started even before the Chinese started theirs, but things just went a bit slower here, and funding didn't come quite as fast. Here in Calgary, we also would like to be part of that. We're building an international quantum network. Well, you'd want to have ground station in many places, not just in Eastern Canada, but also in Western Canada. And here's our ground station. Here you see an example of how it operates. This is actually the Chinese satellite, because that's the only one that's up there to practice with. The green light there is that one, and it's shining down a beacon laser, and we're shining up a beacon laser. And according to Star Wars mythology, we're actually the bad guys in this case. So I don't know if that's on purpose or not, but you know, okay, we'll live with it. So here's what happens during a quantum satellite pass. You have the satellite coming up towards the horizon. You shine your beacon laser in roughly the direction where you expect it to come. It shines it down to you, and then you intercept. You lock on. It's like a camera. It's like following a moving star. And then you start exchanging the quantum signal at a different wavelength that you can split off. And so if you look at, you know, where a quantum satellite ground station was, it was at the edge of campus. They started constructing a whole bunch of things, so we had to move it. But we moved it out to this beautiful place, which is the Rothney Astrophysical Observatory. And now we're up there in our own little building. And here's an example of a pass where we can see how, as time goes by, we have a spike in the number of counts in the quantum detectors that we get when the satellite is the closest, and then it goes down again. And using that, we can do the analysis, and we can start to extract, you know, how much key we get. These may be all, you know, mystery words, but we get 167 kilobytes of secure key, which can then be used to expand a key for actual communication. And here's a Canadian quantum satellite. which Catania is also involved in. And I don't know, 2025, is that a reasonable estimate, I think, is for the launch? Scheduled for 2025 sometime. So, and we'll be serving as one of the ground station of that. So that's where, one of the newest things that we're working on. And then the final sort of few slides here will just be to discuss the medium distance. What if you are sort of less than 2,000 kilometers? You don't have to go across an ocean, but you're not within a city. Well, the losses are still too big to go straight through an optical fiber, but you don't want to use satellites. I'm used to thinking, I come from Denmark originally, and it's like gray all the time. There was one November where I didn't see the sun. It's kind of sad. But then I came to Calgary, and everything was bright, and I thought there's always a blue sky. Then we bought the quantum satellite ground station, and there's so many times that this little thin cloud layer just lingers up there, and it blocks your satellite link. So, I have my doubts that it's going to work for everything, and certainly if you can avoid it, because the distances are not too large, it's better to look for alternatives. And that alternative is called a quantum repeater. For those of you who are in telecommunications will know what repeaters are. They're amplifiers, but we can't amplify quantum states, so we have to do a different thing. So I won't go through this because that takes too long. Even a minute or 5 won't do. But the quantum repeaters relies on these kinds of measurements, joint measurements that I talked about to establish correlation, Bell state measurements. And they serve to distribute entanglement over from small distances, sort of daisy chain it onto a large distance. And what the Bell state measurement is allows you to synchronize this process. But it also requires sources of indistinguishable entangled photons, and it requires a very, very different task of devising quantum memories, things that store quantum states that have been transferred from the light for resting there for a long time. Now, this leads us to the last 3 slides here of other things we do, and a lot of stuff we do in the lab as well is quantum memories, specifically aimed at this task of storing the quantum information. We also do a bunch of other things like post-processing for quantum communications, do some molecular lanthanides experiments. We do biophoton detection because it's about detecting very weak photon signals. We work with microwaves to convert the optical signals into quantum signals that are compatible with superconducting type quantum computers. And we started also using nanofabrication facilities so we can make really small things and not just do big bulky things. And final slide here. This is us from not this summer, but the previous summer, enjoying the blue sky in patches, and also this is always good for attracting people to come here. All right, so that's all I have for today. Happy to take questions if you have any. Yes. Should I bring this one over?
What is next for you and your team in application, in experimentation and application?
Yes, so there's a couple of things. We want to connect to the quantum satellites, the Canadian one, that's the free space mission, demonstrate using Canadian resources, several protocols that will show Canada as a leader and Calgary is part of this interconnected network. I think the main challenges otherwise are on this quantum memory side. It's a very difficult thing to have the quantum information stay put and not be disturbed. As soon as you take the quantum information from light into electron states or spin states, those are all things that are sensitive to magnets and electric fields in their environment or from outside. So things don't stay quantum very long. It all gets mushy and blurred. And so keeping that safe is very, very hard. and especially in a way that also allows you to still interact with exactly the light that you like. So getting those memories to work is a key challenge, and that will allow us to build these quantum repeaters. So making those available will take the quantum networks from being viable only within city limits to something that could be viable, over longer distances. Let's say between Edmonton and Calgary, or even all of the prairies, something like that.
All right, another question. So, how are you funded through the university? Do you how do you get people to take a chance on something so theoretical and then to come up with practicals and practical solutions?
Well, it's funny that you say something so theoretical. I mean, you should see theory, real theory. That's a completely different ball game. I would say that I think there is of course the potential that everybody sees for this. Of course, a lot of people and funders will also see the risk involved in how long is this going to take us. The funding, to be very specific, is through provincial and federal grants, where there's lots of opportunities right now. The federal government has a quantum strategy, national quantum strategy, since a couple of years, which injected a lot of funding into this area to develop it, both businesses and academic research. And the province of Alberta has been very supportive as well, has seen quantum as being one of the areas that really will drive diversification of the economy. So within Canada, the two provinces, very interestingly, that are sort of pushing quantum the hardest are Quebec and Alberta. And we're actually collaborating, who would have thought, right, with Quebec a lot and people in Quebec on building these quantum next level quantum demonstrators.
Right, and the U of C's been really good at spinning off businesses out of the research there. So I mean, you've seen that with QCloud, but are you seeing that the industry partners looking to partner, are they ready to get to invest in the work that you're doing?
I think that would be a good question to also ask the Quantum City team. Because Quantum City really has been about looking at the application side instead of just so is it bottom up or top down? Yeah. And I think that top down, I would say, where the application experts are looking for solutions and they just start hearing about quantum. And that's where Quantum City is about facilitating that connection with the use cases. Whereas the academic part has been very strong for a long time, I would say. As the Institute for Quantum Science Technology, I think it's 2002 that it was instituted at the university.
Great, David. Did you have anything to add on that? You're good. Good.
I saw
Brett.
a hand down there.
I'm kind of curious. I love the turtle with the shell. From the communication side, how would you rank or rate the resiliency of quantum communication?
I mean, I think as we're developing these systems to be more commercially ready, we of course become, as physicists, acquainted with a lot of considerations that we never thought about, how do you secure your whole stack and not just this physics part, right? And I think, of course, as physicists, we could never do that because we don't have the know-how. And the nice thing is about when you start to spin off things into companies is that it enables you to now build a team that has this expertise. Within the universities, like I work together with computer scientists and people from engineering school, but it's always hard to get students between them. I get physics students when they apply for master's and graduate degrees, not engineering or computer science students. So in a company setting, it's much easier to get this whole ecosystem or hold this whole level of expertise on the different parts of the stack together, and then secure this aspect, what we would think are not the novel parts, but are important parts to do right. The quantum aspect of it, I think the protocols obviously are secure, but again, loopholes come, and we have to, just like with any system, we have to protect those loopholes. And I think it's mainly in the context of quantum computers being able to, or maybe some sort of algorithmic advance, being able to erase all kinds of security. It's not like patching a small hole, which is some security breach in a software or some backdoor. It's about the whole basis of our encryption infrastructure being broken. That's what this is supposed to safeguard against. And of course, there's still going to be patches here and there that we have to plug. That will not go away. And people are going to be inherently unreliable as well. They still will be.
That's great. Okay, so I think Daniel, you're joining us on the panel as well.
I believe so, yes.
Good.